Hi, I'm Ioannis, and thank you all for coming. This is getting started with microservices on Kubernetes. It's difficult to start with a couple of words about me. I'm a software developer at Red Hat. I work most of my time on an open source project called Fabricate, which is a microservices platform for Kubernetes and OpenShift. I'm also a member at the Apache Software Foundation, where I've been a committer on numerous projects, including Apache Camel, Cloud Curator, and more. Today I'm going to start with microservices. I'm going to move to Kubernetes. I'm going to try to explain why Kubernetes fits microservices like a glove. And of course, Kubernetes goes hand in hand with Docker, so I'm going to dedicate some slides for Docker too. And then I'm going to move to the more exciting stuff, tooling, frameworks, and technologies that can help you and make your life easier developing microservices on Kubernetes. I'd like to say that this is a clearly developer-focused presentation, and I try to keep the slides minimal and give more attention on examples. So, it seems that today everyone is talking about microservices, but not everyone exactly agrees on what a microservices architecture really is. The definition I prefer to use is that it's an architectural style that allows you to decompose and model a software system into services that provide some sort of business functionality, are isolated and autonomous, and most importantly, are implemented and operated by individual teams, and all of those having their own individual life cycles. So what is the value of microservices? Why are everyone talking about microservices? Microservices is what is enabling an organization to move faster. It's what enabling an organization to deliver features to production faster and more frequently. That is achieved due to having individual release cycles, so each team, whenever it feels ready at their own pace, they can release the new features that they are implementing, and that increases velocity. Also, each team is getting more efficient at what it's doing, because it's free and it's autonomous, and they can select the best tool for the job, the best language, the best framework, the best technologies. And that further increases their effectiveness. And also, splitting a huge development team into multiple smaller ones reduces and minimizes internal bottlenecks and race conditions that happen inside a team. How many times you fixed a bug and wanted it to shift to the production? But one colleague of yours did a version upgrade or implemented something that was conflicting with your change, and then you had to spend a great deal of time in order to communicate with him, to coordinate, and eventually align your changes with his. These are the cases and the bottlenecks I'm talking about, and smaller teams can significantly reduce those cases, if not completely eliminate. Also, an organization is becoming more agile when adopting microservices architecture because services are autonomous, they don't depend with each other, they just call each other. And that allows an organization to shift things around, to move things around, to replace things, add new things, whenever they want. The fact that those services are right-sized and they are fine-grained also makes developing of those services cleaner, and it makes them more testable. So I would say that microservices also increase the stability. Do all this goodness come cheap? No, definitely not. When we are building number of services that are communicating with each other, either using REST or messaging or anything you prefer, in terms you're implementing a distributed system. And distributed systems, by definition, are hard. Also, the large volume of services that you eventually will have to deliver to production increases the operation complexity. So I would say that adopting a microservices architecture style has its own challenges. One of those challenges, most of the challenges derive from the fact that you're building distributed application. One of those is how my services talk to each other and how they discover each other. When I have a service that is not behaving itself, it has flows, issues, how do I discover which is the exact service that causes the issue? How do I do monitoring of my services? How do I do tracing? And things like that. And of course, testing individual services becomes easier in a microservices style, but testing the whole as a big bang is something that gets way more complex. And of course, it's the delivery complexity that I've already mentioned. Docker could be a potential solution to the delivery challenges that goes with microservices. And I'd like to say a few things about Docker. What is Docker? Docker is a containerization platform which allows you to package your application, to seed your application, and to eventually run your application. For packaging, Docker is using the notion of Docker image, which is a description of what is your application, what are the requirements of your application, what is the execution environment of your application. Are you using an application server? Are you using a serverless container? Whatever. All these are stuff that are well defined inside your Docker image. And also, maybe operating system dependencies, like libraries and stuff. All these are part of the Docker image. How can one create a Docker image? You usually create a file called Docker file, which contains a set of instructions that describe exactly how your application should be packaged. We saw an example in the previous presentation, and I intend to show one later. Once I have my image ready, I'm able to push it to either a private registry or a public registry, and distribute this way my image to my colleagues, to other teams inside an organization, or to the public, depending on what my needs are. And then, when I have my hands a Docker image, I can run it and run my application inside an isolated environment, which is called container. The container is an isolated environment with its own network, its own file system, and is an instance of the Docker image, I would say. And the idea and the model of the container is really, really helpful in the microservices world because it promotes reproducibility. You don't suffer from issues, it runs here, it doesn't run there, and etc. Some examples of Docker container. This presentation is actually running on Docker. This is an HTML5 presentation which is served by a web server that has been packaged and is running inside the Docker container that's running on top of Kubernetes. But if all this sounds a little bit voodoo, I would like to start clean and create a new application from scratch and demonstrate how one can Dockerize the application. I'm going to use Vertex, mostly because Vertex is a framework that is not verbose and it's a good fit for getting started or a Hello World example. And I'm going to create a Hello Thessaloniki example. Okay, I'm creating a directory. Let me take a second to start. I would like to say that Vertex, I forgot to mention that Vertex is a framework for creating reactive applications. It's a good fit for microservices, and it's also polyglot. So in this particular case, I could write my code in JavaScript, and my hello world will be as simple as that. I'm creating a simple HTTP server, and I'm adding a request handler that accepts a function and will bind on port 8080. Inside the function, I will accept requests and respond with a simple string message, which is Hello Thessaloniki. Okay, I now can save my file, and I can use the Vertex binary in order to start and test my application. The application is running, and I can use curl to access localhost 8080 and verify that Vertex responds with the right message. Okay, how can one Dockerize as an application? I already mentioned about the Docker file, so I create one. And I will define inside my Docker file the parent image that I'm going to use and extend. And I'll use Vertex 3, which contains the JVM that I'm going to need, which contains all the Vertex libraries that are required. And all I have to do inside my Docker file is to define which is the JavaScript file that I'm going to use, and where exactly I want inside my Docker image that JavaScript file to be copied. I'm making sure the directory exists, and I'm copying the JavaScript file from my local file system to to the Docker image. I'm specifying the working directory, and I will also advertise that I'm exposing port 8080, and of course, in the end, I need to tell Docker how to run my container. So I'm specifying that I'm going to use a shell command, and I'm specifying the actual command, which is vertex run, the name of the script that I created, and my class path. Okay, we are set. Now I can read my Docker file and create an image. I will name the image Ioannis Kanellos. And once the image is ready, I will create a container out of the image. All I need to do is to do a Docker run. I will port forward the host port 8080 to the container port 8080 so that I can access the service from my laptop. I can do a PS and see that the container is indeed running. And then I'm ready to do the HTTP request. I'm using curl on localhost 8080, and I get back the hello Thessaloniki message again. So there are obvious resemblances between Docker containers and VMs. As already mentioned, Docker containers are much more lightweight. They don't carry the operating system burden. So what I want you to remember is that Docker containers have a very tiny footprint. They are extremely fast. One is able to run on a single host tens, hundreds, if not thousands Docker containers. And they promote reproducibility, which is an invaluable tool. Does Docker solve all of our problems? No, of course not. We are talking about distributed systems. We are talking about microservices. So we need to run our containers on multiple hosts. So one could say, why don't I run multiple hosts running Docker? And this is something that one could do. It's not hard. But one would carry them the burden of scheduling the containers on multiple hosts. And that is not an easy task to take. Here is where Kubernetes comes into place. Kubernetes helps you schedule your containers on multiple hosts, and efficiently is a container platform that allows you to deploy your applications quick and predictable, but also help you scale your application and roll out new features. The high level of Kubernetes is shown in this diagram. As you can see, we have one or more containers living inside a unit that is called pod. And Kubernetes can distribute those pods on multiple hosts, which are called minions. And I think that nowadays they have been renamed to nodes, if I'm not mistaken. All of those nodes and the distribution is handled by the master, and our containers communicate with each other with services. I will dive in and try to explain all of those concepts one by one. I'll start with the pod. The pod encapsulates one or more containers, as I already mentioned, which have the following characteristics. They serve network, and they can potentially insert file systems through volumes. Why one would want to have multiple containers living inside a pod? One use case could be that I have a container that requires local host access to a service provided by another container. Or another use case could be that I want to enhance capabilities and the behavior of an existing container using another. A real example of the later use case is the Jenkins container, the Jenkins slave container, which can be added in the same pod with a Maven container, so that we can add Maven capabilities to Jenkins slave. This actually is a pattern that is used right now by the Jenkins Kubernetes plugin, and it's really, really helpful. So, how do hosts talk to each other? Using services. Services is a resource, a Kubernetes resource, created by the user and communicated to Kubernetes that actually defines two things. The first thing is a selector, and the selector is responsible for finding out which are the pods that are providing the service, and the second are details on how one can connect to the service. When a user creates the service on Kubernetes, Kubernetes will actually create some sort of proxy that will sit in front of the service, and it can do a lot of helpful things like load balancing requests if I have multiple pods providing a service. From the user point of view, a service is something that can be accessed using DNS. Out of the box, Kubernetes uses a DNS add-on, and for each service that you deploy on Kubernetes, it will create an entry, so it makes accessing services really, really easy. And of course, it's scaling, right? I mentioned scaling on one of the key features of Kubernetes, and how scaling is achieved? It's achieved through the replica set. A replica set is, combines two things. The first one is the definition of a pod to play, and then the second is the number of instances of that play that I want to run on Kubernetes at any point of time. So, in this example, I'm requesting 3 replicas, and Kubernetes is creating and distributing to multiple nodes 3 instances of the pod that is defined out of the play. If for any reason one of those pods die, if for example I kill one accidentally, Kubernetes will make sure that the 3 replicas requirement will be satisfied and will replace the pod that I accidentally killed. If for any reason the node that is hosting my pod dies for any reason, if one pulls a flag or whatever, Kubernetes will schedule a new pod on one of the remaining nodes, if any. And of course, even in cases where my pod seems to be running, but is not behaving itself, it has some sort of internal failure, Kubernetes can potentially replace that if we define some sort of health code, which is either an HTTP request or a TCP connection or a command execution that is able to determine if my pod is healthy or not. A more high-level resource than replica sets is the deployment. And the deployment is controlling and creating replica sets for me, and allows me to roll out new features, roll back, things like that. I could go on and talk about more of Kubernetes stuff. There are tons of resources and tons of options for the user, but I think that it would be nice to stop at this point and give us some time to digest. So, how one can run Kubernetes? Kubernetes comes in many flavors. It's something that you can download from the internet and install on your laptop, on your local network, on your local cloud, on a public cloud. You can access Kubernetes through Google Container Engine, or you can use other kind of distributions of Kubernetes, like OpenShift. OpenShift is a platform as a service, which is basically a distribution of Kubernetes, which you can also install local on the cloud or whatever, or you can use a hosted version. The options here are unlimited, and sometimes it's frightening. Personally, I think that if you want to get started with Kubernetes right now, your best bet is to go with Minikube. And Minikube is a single binary that you download and you save on your file system. And using Minikube, you can start a local Kubernetes cluster in no time. And I'd like to show you that in action. I'm running Linux here. I've already downloaded Minikube, and I'm using Minikube. I'm telling Minikube to start. Oops, okay. I'm specifying the memory that I want to use, and also specifying the VM driver that I want to use. Since I'm on Linux, KVM is the obvious choice, but there are other options if you are on Windows or if you are on OS 6 or whatnot. After a while, Minikube will spin up a Kubernetes cluster for me, and I'll start and use it right ahead, and I'll create for a deployment descriptor for the Vertex application we created. I'm creating a deployment.yaml file, which is a descriptor of the deployment. In Kubernetes, we either use YAML or JSON, but I prefer YAML because it's easier to the eye. And I'm creating a resource which is called a deployment. I'm going to name that resource Hello Thessaloniki. And then I'm going to add the specification of that resource. I'm going to specify the number of replicas that I want. And then I'm going to specify the code template that I want to use. I will add some metadata, and in particular, I will add a label. that is a key value pair, and in particular case, it's app equals Thessaloniki. And this label is something that can be used by services in order to discover my service. I already mentioned the selector. The selector discovers faults by comparing labels, right? And then it's time to define the containers that I want to live in my pod. And I will add a single container that I'll name Hello Thessaloniki, how original of me. And I'll add a single image, which is the Docker image that we created in the previous step. And I'm also going to expose port 8080. The reason that I need to define that I'm going to use port 8080 is that some services that will use that port know exactly how they will connect it. I'm using the Kubernetes command line interface, which is kubectl, and I'm creating the resource of my Kubernetes. The resource has been created, and now I can wait until all the pods that are defined in the resource have been created. My resource is up and running, and now I can try it out. But before I try it out, I will have to port forward again from localhost 8080 to the pod. And I'm going to use curl again to access localhost on port 8080 and verify that the response I get is Hello Thessaloniki. So, I'm a software developer. This is a developer conference. So, I assume that most of you are developers, right? And everything I demonstrated so far is not really developer-ish. It seems more operation-focused. Well, the truth is that creating Docker files that resemble like shell scripts or hacking spooky YAML descriptors does seem to me like operation focused. And what the developer really wants, at least I know what I want. I want to start hacking code as soon as possible. No old stuff, no descriptors, no things like that. Luckily, there are tools out there that can tone down the old flavor in the whole Kubernetes and Docker world. And one of those is the Fabricate Flavor plugin. The Fabricate Flavor plugin is a tool that can automate the image building process. It can automate the generation of the Kubernetes resources. And of course, it can automate the process of deployment, debugging, and more. Especially the last bit is something that makes Kubernetes look like a typical application container, like a server container or an app server, and things like that. Why don't we see that in action? In this example, I'm going to move away from the Vertex application created in the previous step, and I'm going to create, using the Spring Boot CLI, a Groovy-based Spring Boot application, web application. The application is ready, and the only thing I have to do for this application is to use the Fabricate Flavor plugin and invoke the setup goal. And the setup goal will open the BOM of my project and will register itself inside the BOM, so the Fabricate Flavor plugin can take care of the process of building the image, generating the resources, deploying the application, and things like that. One thing that the Fabricate Flavor plugin does not do for us is writing the code itself. So I'm going to take a minute before I try out the plugin in order to write some code. Well, I will sit here, I will not write the code, but I will copy-paste the code from my cheat sheet. And the code in this example is a simple Spring Boot REST controller, which has a single mapping from slash to hello. And hello is just a function that is returning Hello Thessaloniki using Spring methods. Okay, let's save that and move on. Okay, I'm good to go. Now, using Maven, in a single go, I will create a Docker image for my application, I will generate all the required Kubernetes resources, and I will deploy the application. Usually the first time, it takes a while, mostly because Docker will have to download things, but the second time you will run it, it's really fast. In this particular run, I think it will take 80 seconds. It's really, really fast. And I can use the command the Kubernetes command line in order to verify that my application has been successfully deployed. As I can see, it is in run status, but it doesn't seem to be in ready status. I will have to wait a little longer, but while I wait, let me ask you a question. How does Kubernetes know if my application is ready or not? Well, the answer is that, like the health codes that I mentioned earlier, Kubernetes also has the notion of readiness probes. And those readiness probes can be an HTTP request, a TCP connection, a shell command, or anything that can determine if my application is in ready state or not. Oops. Let's wait a little bit. So, we're building a Spring Boot application. The fabricating element again is able to understand that we are building a Spring Boot application. And when it identifies the Spring Boot application, it will add inside the pod definition the readiness probe that is required for letting Kubernetes know that Spring Web is able to serve requests. So this is a really cool feature. We don't have to write any code, we don't have to do anything. So after a while, the application went, after 21 seconds, the application went in ready state, and now I can use it. I will use the same drill again. I will port forward from localhost 8080 to my pod, and then I'm using a curl to verify that the message is this time, hello Thessaloniki using Spring. So why Spring? Thank you. Why Spring? The primary reason that I used Spring in this example is also because it's not verbose and it's something that can easily fit in an ASCII cast like the one that you just watched. Another reason is that I'm a little bit biased because I'm actively involved in a project called Spring Cloud Kubernetes, which is an implementation of the Spring Cloud abstractions for the Kubernetes world. But what other options do developers have? What other tools and frameworks one can use in order to implement microservices? Well, the answer is everything. You can use everything. But the most popular options out there is Wildfly Swarm. Dimitris Andreadis at 3 has a presentation about Swarm. Be sure to check it out. And also Drop Wizard, which is also quite popular. And Lagom is a new framework, is a new player in the game. It's not so famous yet, because it's new, but I thought that it would be a good idea to mention it. The next step is to implement more features, but while I'm implementing features, I will have to add some sort of test coverage and things like that. How do I test an application? How do I test my microservices that are running on Kubernetes? There is a framework called ActiveMQ, a testing framework, which usually runs on top of JUnit or TestNJ or whatever you are using. And it's a framework that was became especially popular when application servers were really popular because it allowed you to test your application servers in an easy way. The ActiveMQ team recently created a new project which is called ActiveMQ. And it's a testing framework that this time does not aim application server, but it aims containers. Recently, there's a new entry, a new extension in the ActiveMQ project, which is called ActiveMQ Kubernetes. And this extension helps you write tests. And when you run your test, it creates a session. It deploys your application during that session. It will wait until your application reaches ready state. And then it will start and bootstrap the test suite. And at the end, when your tests are done, it will clean up so that you leave nothing behind. So what exactly is a session? A session is the interaction of ActiveMQ with Kubernetes. It serves the same life cycle with a test suite. So for each test suite, you will have a single session. And inside that single session, ActiveMQ will create a Kubernetes namespace, new word. What is a namespace? A namespace is an isolated area inside your the Kubernetes cluster in which you can deploy your stuff without messing or interfering with things that are running on other namespaces. So what happens inside an ArchiVM session stays inside the session. What can you test using ArchiVM with Kubernetes? You can validate that your Docker images are correct. You can validate that the Kubernetes resources that you generated or handcrafted are same. And then, of course, you can deploy your application in a test Kubernetes environment and interact with it. So, for example, one could create an ActiveMQ Kubernetes test, spin up a test application, and then run Selenium tests on top of that, or whatever. When we try and add some tests in our application, and I will have to pop my IDE right here. It takes a while. And I'm opening the application that we created in the previous step. The first thing that I need to do is to define inside my POM a set of dependencies, which are the ActiveMQ Kubernetes dependencies. It's actually 3 jars that I need to add inside my POM. And then I can create a test. I need to specify the Archelian runner. And the actual test, what we'll do is that we'll access the service that is created and generated by Fabricate by the plugin and deployed to Kubernetes, and test in an automated fashion that we get back the expected result. So I need to grab a URL of that service right here, and I'm defining that the name of the service is Voxxed Thessaloniki. And then, of course, I'm asking Archelian to do the port forward trick that I did on the command line too. And I'm also defining that this should be treated as an Archelian resource, and I want Archelian to inject that URL in my test. Let's go to the actual test case right here. I'm creating an instance of an HTTP client, and then I'm defining that I want to do a simple HTTP GET request on the target URL. And then grab the response and assert that it is equal to the expected response, which is hello Thessaloniki using string. I'm going to run a maven clean test and figure crossed that it will work. Fabricate maven plugin spins up, generates all the resources, and then the Archelian plugin kicks in. It initializes the session, it creates the namespace that I mentioned right here. It detects the Kubernetes resources that have been generated by the Fabricate maven plugin, so there is interoperability here, which is really good. It deploys those resources on Kubernetes, and now we're seeing that we are waiting until the container starts up, and until the service can find a ready pod providing the Voxxed Thessaloniki services. Everything seems to go fine. Test was successful. So we have our first test. Okay. Regardless of what your test coverage is, regardless of how many unit tests and how many integration tests you write, in a distributed system, you will always have to deal with problems, and you will always have to troubleshoot. So usually, in a distributed system, a user will interact with your system, maybe using a web interface, and that web interface will call a service, and that service may call one other service or more services, and those services, you understand the drill, right? So we actually have a user that is initiating a request, and then we have a tree of service invocations. What happens when something fails in that tree, when a node fails? What happens when a node in that tree becomes unresponsive? If particular service fails and becomes unresponsive, in the worst case scenario, the user will get an error message back. In the best case scenario, the user will get an error message back. But in the worst case, the user will wait for a very long time until he gets the error message back. And that's not really the user experience we should be aiming. So, the last couple of years with the rise of microservices, a new pattern has been becoming really popular, and that pattern is the circuit breaker. The circuit breaker is something that you add in front of your service invocations, and the circuit breaker will monitor how the remote service is behaving. So, if it notices that you have too many errors or timeouts in a short period of time, the circuit breaker will open, the circuit will remain open, so you will no longer call the faulty service. What will happen then? You will have the ability to fail fast without even having to wait until the service timeout. Or, if you've configured a fallback service, you will be able to fall back. One of the most popular implementations of a circuit breaker is Hashrix, which is an open source project provided by Netflix. If I have time, I will show you the Hashrix dashboard in the end of the presentation. I would like to say a few words about the distributed tracing. If a service fails and timeouts, that's one thing, but there are also cases where the signs are not so obvious. So you may have a service that becomes slow. How do you find inside the invocation tree which is the node that became slow? How do you troubleshoot latency issues? How do you detect bottlenecks? And things like that. Distributed tracing is the answer to those questions, and it is actually the process of collecting timing information about the service invocations, how long did they take, and things like that, which you can then aggregate, correlate, process in order to determine which is a service that's misbehaving. And one of those distributed tracing systems that are out there right now and are really popular and play great with Kubernetes, one of those is Zipkin. I have my Zipkin dashboard open right here, and I also have some services running in a generator that generates requests so that I can demonstrate some things here. And I can go to the dependency graph, and I can see the invocation chain I mentioned earlier. So we have, in this example, service A calling service B, calling service C, and these are things that are traced by Zipkin. So I can select any of those services, let's say service A, and I can ask to find all the traces that we have in the last day. Okay, then I can pick any of those traces, and I can see a very, very, very nice scheme here, which demonstrates the path, the request path. It shows me all the services that participate in the request, and on the right side, I can see exactly how much did it take for each service to respond. So, using Zipkin or using any other distributed tracing tool, I'm able to find very useful information about latency-related issues. And of course, I also mentioned the Hashrix dashboard, which is a visual aid for Hashrix. And I can use it in order to monitor the state of my circuit breakers. So I opened the Hashrix monitor, and I'm seeing all the circuit breakers that are running in my cluster. How the Hashrix monitor know which circuit breakers are running in my cluster? Hashrix is using a service, a helping service that is called Turbine. And Turbine has the sole purpose of discovering and aggregating Hashrix metric streams. So in our case, the Turbine server that we are using discovers all services that are running in Kubernetes, all pods that are running in Kubernetes that are able to expose Hashrix metrics, aggregates those so that we can have this beautiful eye candy. Both the Zipkin and the Hashrix dashboard are things that I installed in my local cluster using the Fabricate console. The Fabricate console is a superset of the typical Kubernetes dashboard. It's more developer focused than the Kubernetes dashboard, but it also features a really nice marketplace or app store, or call it whatever you want. And you can find in here services that you can install with a single click on your cluster. It's something that's definitely worth checking out. And of course, I would like to say just a few words about CI and CV. As I mentioned in the previous talk, microservices go hand in hand with CV, but in order to talk about CV, I would have to spend maybe a whole presentation. But if all those things are of interest to you, CI and CD are stuff that you definitely need to explore. The Fabricate project, which adds a lot of tools to Kubernetes and OpenShift, does provide continuous delivery pipelines that can be used in Kubernetes and is really useful. And in the end, I have some resources that will be very useful to you. The first one is a book which is called Microservices for Java Developers. It's written by Christian Postman. It's a colleague of mine. And the book is something that you can download for free from the Written Developer Network. And also some other resources. First one, the project Prometheus, which can be found on GitHub. It's a project for collecting metrics for your microservices. It's really useful. It plays great within Kubernetes. Also, Kubeflix, which is a project that implements most of the popular Netflix framework integrations for Kubernetes. And of course, Kubernetes Zipkin, which is what powered the Zipkin dashboard right here. Last but not least, this presentation can be downloaded for GitHub, or if you prefer, you can grab it directly from Docker Hub using this address. And this is it. I don't know if you have any questions.
Do you have any? We will get only one question, and you can find Ioannis during lunch.
Hi, Ioannis, thanks a lot. Well, you said it yourself, distributed systems are hard. What would be some cases where you would advise people not to go to a microservices architecture?
I have an issue with the mic. Okay, it's back on. So, yes, maybe I should have added a slide for that. Microservices is definitely not for everyone, and it's not a silver bullet for all the problems in the world, right? If you need the increased velocity that your microservices provide, then you should definitely check into microservices. But if you can live with a release cycle that can take weeks, months, and things like that, then yes, microservices may not be the best solution for you. But if you want to have the ability of pushing new features and fixes and things like that daily into production, then I would surely advise to look at microservices.
Because it sounds to me that, it's adding a lot of complexity.
Yes, it does. It does. It gives great value, and this is something. This is why it's something that has been adopted, like from companies like Netflix, Amazon, and things like that. But it does add complexity, and this is why the need of such presentations to demonstrate tools to fight that complexity. So, I don't know. Did I answer your question?
Yeah. That's a good thing.
You will have all the time to discuss.
Okay.
Before we go, check Interworks Cloud Draw. There is very cool stuff in the draw, like Microsoft Office, a Nokia Lumia phone, and stuff like that. And also there is free beer. So see you here in around 40 minutes.
Okay.
Thank you, guys.